Thanks, Daniel. That was a nice talk. Any questions for Daniel?
Can I ask a technical and a non-technical question? When you were doing the uniform field case, I think you said, I might be wrong, I think you said the alphane speed was constant. Is that right?
That's right, yes.
But don't you have, how does that work? Don't you have a, but n was not constant. What's your...
Yes. So we're in the Boussinesq approximation here. So the to leading order, the density is constant, but there are small perturbations to that, which are important when in terms of when they interact with gravity, but they're not important for the alphane velocity.
Right. Okay. And what is the magnetic mode? I think you said it was a slow mode.
Yeah. It's a slow magnetosonic wave because we're doing this in 2D. So I think that there's not going to be any alphane wave because you can't have any perturbations perpendicular.
But you're incompressible.
Yes. Yeah. So I mean they're equivalent.
I've not heard those waves referred to as magnetosonic waves in incompressible cases before, but I guess it would correspond with that if you.
Yeah, I guess the point is that there's two polarizations. You can have perturbations which are right. So you have a plane made of the wave vector and the magnetic field. And I think the alphane wave is the displacements are perpendicular to that plane, and then for the slow magnetosonic wave, the perturbations are within that plane. So, I mean, honestly, I'll tell you that in our first draft of this paper, I called it alphane waves, and then I sent it to Ellen Zweibel, and she told me that they're not alphane waves because they're the perturbations are in the same plane as the KB plane, and that I should switch it to slow magnetosonic waves.
No, I think they are alphane waves. I think they're what are they called? They're called like shear alphane waves or something. I mean, magnetosonic, you have to. If you do the magnetoacoustic waves, then you have to take, one of the starting points for magnetoacoustic waves is that div u is non-zero, right?
You mean that the sound speed is non-zero? Right. Sorry, u is not zero.
Div u.
Yeah. Oh, yes. But then if you take the limit that the sound speed goes to infinity, then it's going to give you the same dispersion relation as the alphane wave. So that's what we're doing here.
Okay. So this middle region, this field region, you said that maybe it had a strong field because of a dynamo. Is that still is the idea that that's still going on, or is this a field that was generated in the past?
Yeah, so that's a great question. The presumption here is that this is a fossil field generated when the star was on the main sequence and had a convective core. It's supposed to have generated some magnetic field, and then once the convection stopped, that field kind of diffuses and presumably will go into maybe like a Taylor state or some other like a low, relatively low L field that will persist for a long time. So we're not imagining that this field is being regenerated. We're just supposing that it's left over from the convection that happened in an earlier phase of stellar evolution.
Right. So one presumably could estimate how strong that field is if
That's absolutely right.
With equipartition, let's say, in the dynamo, and then it kicked. So is that done? Is that how it's done?
Yes, that's exactly right. So you assume some equipartition field when the star was on the main sequence, and then you assume that there's like some flux freezing or something as it evolves on this red giant branch, and if you do that, then you end up with a magnetic field, which so happens to exactly correspond to the field strength which is needed to get this sort of interaction with the internal gravity waves.
Okay, great.
So it kind of seems to fit together. So those types of estimates were made in a paper, I think by Jim Fuller and Matteo Cantiello, which was published in Science a few years ago.
Great, thank you.
Stephen, you had a question?
I think I've got a couple as well. Hi, Daniel.
Yep.
So the first one sort of follows on from David about the constant B variable N simulations.
Yeah.
So you had your layer where, or your level where something special happens.
Yes.
And I guess that's something to do with the choice of N. So, I mean, you could consider, say, N decreasing with depth or N increasing with depth.
Yes.
What's the condition on N, which I guess also relates to the magnetic field strength for something special to happen? I mean, can you get scenarios where nothing special happens?
Yes, absolutely. So, basically the idea, so the specific case that I had was, I think, n increasing with depth.
Yeah.
And the idea is that as n increases with depth, the vertical wave number also increases. If you didn't have a magnetic field. Now, if you didn't have any stratification and you just had the magnetic field, then there's for a given frequency, there's just one vertical wave number, and basically the interaction happens if the vertical wave number associated with the internal gravity wave by itself would match with the vertical wave number associated with the magnetic field by itself, and that requires for n to be increasing enough or for B to be strong enough.
Okay.
So the way to physically think about it is for actually now that I'm saying it, I think I have it backwards where n was decreasing with depth in order to have the kz increase with depth. It's easy to sort out which direction it is.
I think you had it right the first time.
Whichever one.
The frequency is like nkx over kz roughly. So if kz increases, then n increases as well.
Yes. Okay. Good. Yeah. So the kz is increasing as you go down, and then basically eventually that's going to hit the kz associated with the magnetic field, and the smaller the magnetic field, the larger that kz is. So if the magnetic field was weak enough, then the wave would propagate all the way to the bottom, and like in a star, it would just reflect off the bottom. In our simulation, we put a damping layer, so it would have damped. If we had put like a no-slip boundary or something, then it would have reflected.
So my second question sort of is kind of in that same zone as well. So my very limited understanding of helioseismology is that you're basically looking at normal modes. So you're looking at, you know, a spherical object, and you seek the values of omega for which that oscillates freely. And then these are the things you look for in the seismology, helioseismology. And of course, the problem or the detailed problem you described is quite different, because it's a forced wave problem with things going down, maybe some evanescence, maybe something coming back up. So it's not like a sort of a global mode in the sense of a normal mode. So I just wondered if you could say something about the link between the two.
Yeah, that's right. Yeah, thanks for asking that. I guess I didn't make this sufficiently clear in the talk, but the idea is that if you had a wave which is propagating downwards and can just reflect up, then that's something that could then set up a global mode. Okay, so that's something that you would then be able to see at the surface. If you have a wave which goes down and then as it goes back up, it's like a magnetic wave, and it goes to very large wave numbers, and it's going to get damped out, then that's never going to make it to the surface anymore. And because of that, there's not going to be any global mode associated with that. So you're not going to see a signature at the surface. So you're right. I mean, I didn't do this in terms of like an eigenvalue analysis, which I mean, especially in the constant magnetic field case, I mean, you could do that. It would be pretty straightforward. But I guess once you have horizontal variation in the magnetic field, it becomes like a 2D problem. And I guess that the hope was that doing these force simulations would give you enough intuition for like the mechanism of what's going on.
Great, thank you.
Thanks. Any further questions? Chris, did you have your hand up, or have you put your hand down?
No, I did. I did have a question. I've got a quick question, if it's okay. Yes. Can you hear me?
Yes.
Yeah. What sort of strength of magnetic fields do you actually need to get this mechanism to work in order actually to get rid of these waves that are actually propagating down? I mean, I would imagine they're pretty strong, aren't they? I mean,
Yeah. So I'd say that the chance that I get this right is maybe like 50-50. I think it's about 10 to 5 Gauss.
Oh, right, that is huge.
But if you do an estimate of equipartition magnetic field from convection for a main sequence of a massive star, and then you use flux freezing to convert that into what happens when it to give you like a fossil field strength when it's a red giant branch star, you get numbers of this sort.
Oh, I see. So there is a sort of condensation of the core of the star, which is the way in which it might get up, like it's almost like a pulsar. I mean,
that's right. Yeah.
Yeah.
I mean, not nearly as extreme, of course. But.
No, not as extreme as that, but the same sort of principle gets you up to 10 to the 5. Because I mean, that is an enormous field, isn't it? I mean, people usually sort of 10 to the 4 is considered to be a very big field for a solar model, isn't it?
Mm-hmm.
Yeah.
Okay. Yeah, and I think it's that contraction that gets you up there.
Yeah. Okay. Thank you.
Yeah, and again, for more details on that, I would point you to this paper by Jim Fuller and Matteo Cantiello.
Yeah. Thanks.